So in this video, we're going to talk about the definition of the derivative, specifically where it comes from. And to motivate this derivation, we're going to take a look at this graph. So we've got this graph of a parabola, and you'll see that at the location where x is 1, we've got this line that is intersecting the parabola and is traveling the exact same direction as the parabola does. That's called the tangent line to f of x at that x coordinate. Now, all of the questions that you see at the top of this screen have the same answer. So the way that we would develop that answer to each of them is going to be with the same process. So the first question is, what is the slope of f of x at 1? You see the same parabola as on the last screen, and whatever the slope of this line is, and I've already gotten the tangent line graphed with the function, so you might be able to try to do a quick rise over run calculation on this to try to estimate it. But how do you handle this if you don't have access to the graph? That's what we want to get to within this video. What is the slope of the tangent line to f at 1? I think that's the question I actually asked on the last screen, right? Slope of the graph, slope of the tangent line really mean the same thing. Generally, if a function has some sort of a context behind it, the slope of the graph at the x value you're considering is the instantaneous rate of change of that function at that value. So this function x squared plus 1, standard run-of-the-mill parabola, shifted 1 unit up from 0, 0. We see that it has a positive slope at 1. Obviously, the tangent line that's drawn in here has a positive slope. How can we try to approximate its slope without necessarily having access to the graph? Having access to the graph, we can try to figure out a couple of ordered pairs on the graph. We could do a rise divided by a run, and we can estimate our slope pretty effectively. What if you don't have the graph? So if we want to estimate the slope of this function at 1, or estimate the slope of the tangent line to this function at 1, what we can do is we can do regular slope calculations. These are referred to as secant lines that you see I've drawn over here. So if you look at the red one has an ordered pair 1, 2 on it, and then the other ordered pair 0, 1. So what I did is I did a slope calculation that involved the x value that I wanted to establish my estimate at, and then I picked another x value that was 1 unit either to the left or to the right, doesn't matter which direction you go. I went 1 unit to the left of the x that I want my calculation to be based at. And I found the corresponding y's. I found this y by plugging 1 in place of this x, squaring it and adding 1. I found this y by plugging 0 in place of this x, squaring it and adding 1. Doing that first slope calculation gives me a result of 1. Now here's what I want to do. What I want to do is I want to squeeze the denominator of this calculation closer and closer and closer to 0. Because if I squeeze the denominator closer and closer to 0, what's going to happen with this sequence of calculations is I should be getting an answer that's getting closer and closer to the slope of the tangent line. And so I bumped from an x value of 0 to an x value of 1/2, found the slope of that secant line, right? So I found this y value by putting 0.5 in place of x, squaring it and adding 1. I got 1.5. I then bumped it even a little bit closer. So I kept that first ordered pair the same because I wanted to base this estimate at the x of 1. So I didn't move that ordered pair, but the other ordered pair that I did within each slope calculation is getting closer and closer to the x value where my calculation is based. This denominator is 1. This denominator is 1/2. This denominator is 1/10. As delta x in my slope calculation approaches 0, the slope of the secant line seems like it's trending toward 2, and that's how we can estimate the slope of that tangent line. Now, how do we get away from having to estimate the slope of the tangent line? How do we actually find it? And that's really the main point of this video. So here is the situation. We want the slope of the tangent line to a function at the x value of a. So what I'm going to do is I'm going to basically think about what we did on the last screen, and that was regular old slope calculations, right? y2 minus y1 divided by x2 minus x1. And then I tweaked the slope formula a little bit. You might not recognize this as obviously being the slope formula as this one would be, but what we can do, if I pick my x values to be a and b, I can change the denominator to b minus a, And then in the numerator, rather than using just y values, I can use function notation, right? The y value at a is going to be f of a, and the y value at b is going to be f of b. Now, what we would like to have happen here is we would like to have our denominator to be a single variable, because if we can do that, we can use limits to force this to happen without having to go through the progression of calculations that we did back here. So I'm going to pick the letter h, and I'm just going to let h equal this denominator. So if h is equal to b minus a, my slope formula transitions to this. Doesn't look as much like the slope formula anymore, but it really still is. Issue with this, it depends on more than I would like it to. It depends on b, it depends on a, and it depends on h. I can use this assignment for h to figure out what b is equal to. If I add this a to the left side of the equation, I'll get positive a plus the h that's already there. That's what b is going to equal to. So I can substitute a plus h in place of b. This is really just the slope formula. It's been tweaked to our advantage, and what we can do with it now is we can force the denominator of the calculation to approach 0 with a limit. So if I check the limit as h approaches 0, you might recognize what's here as a formula from your calculus course that you've said is going to compute the slope of the tangent line, or is going to represent f prime of a. This is the definition of the derivative for a function evaluated at a. If I swap out the a's for x's, what I end up with is the definition of the derivative. Now, for those of you well into your calculus course, using this definition is probably not what you're doing any longer in order to take derivatives. What you do shortly after you learn this definition is you develop rules that are proven with this definition to always work, to bypass always having to use this. Now, in the next few videos, you'll see a few examples of me actually using this to produce some derivatives with the definition, but I want to make sure this initial video here, we talked about how to develop this notion, how to develop this definition.